Hi everyone, welcome back to Workshop, and it's part 2 of the HP 34401A 6.5 digit multimeter repair. In part 1 you saw me tear the meter down, investigate an issue, scope as part of the circuit board, and replaced some electrolytic capacitors, and then determined that the actual display had a fault as well. And so I went offline, went and put an order in for a replacement VFD, got that from China via eBay, so it's obviously not going to be a HP part, it's going to be something else. So it arrived in the mail today, so we're going to tear down the display, get rid of the old VFD off it and replace it. So here's the original, still soldered onto the display board here, and I'll bring in the new one that's just come in through the door, and it looks more or less identical. It's obviously meant for the 34401A, it's got the same legends on the display there, everything looks the same, but when you zoom in close you can tell it's not an identical part, so it's obviously been made somewhere else. And the legs on it are a little bit differently formed. These are sort of bent over pins. As you can see, they're flat pins that come out sideways from the actual glass and then bend over sideways, as you can see there. On the original one, that doesn't seem to be the case. You've got a slightly wider glass by the looks of it, and the legs just pop out down vertically straight from the edge of the glass. But the important thing is the footprint is the same. It is roughly the same width. You can see there I'm lining up the pins on the VFD with the holes in the circuit board, so it is designed to go into this board obviously. Where these come from, I don't know. It always surprises me that these are pattern parts that somebody makes and goes to a lot of trouble to manufacture replacement VFDs, non-HP Agilent branded for these old multimeters, but unless this is some sort of secondary batch or something that's flying around, I've got no idea. But let's just hope that when we fit it to the board it works. It was sold as brand new, but you never can tell. The pins don't look like they've been soldered, but that may just be a case of cleaning up really well. Who knows? I have heard reports that other people have bought replacement VFDs and they've not been the brightest things in the world, or they've not lasted that long despite being nice and bright at the start. So we'll see how this goes. We'll take it from there. So let's go and first of all strip the old one off of the circuit board, ready for the new one. So to remove the old one, the first thing I'm going to do is actually tin up the old solder pads there right round the whole of the VFD. And the reason I'm doing that is this board's actually quite old, you know, it's many decades old, so I do want to give the solder sucker a good chance at being able to suck the solder through these through-hole plated boards. And with old solder, that's not necessarily the easiest thing in the world. It's much easier if you re-tin up all the joints, at the same time adding a little bit of flux. It gives the best chance possible for removing the old solder and letting the VFD basically fall out. There is actually two metal brackets on both sides here, as you can see. I'm going to leave them in situ. They're more or less just guards. They're not really getting in the way of holding the VFD in place, so I should manage to remove it without removing those metal plates. You don't want to be too slow at resoldering these joints, because you don't want the solder to go down through any more than it already is, so be quite quick with it. Okay, that's the desoldering done, so let's see if it comes off. So I'll go over all the holes, have a quick inspection of them, make sure that the pins are not actually still stuck to the sides of the through hole plating, usually just by giving them a little push, and sometimes you hear them click sort of thing, and sometimes you'll see them just sort of snap into the centre of the hole from being sort of like still stuck to the sides of the hole. And so far I've just had a couple, the rest do appear to be free and clear. Okay, but now before I actually go and try and pull it from the board, you'll see on the metal bracket here there's a couple of tabs. They're just bent over to stop the glass from raising up, so I will need to bend them out slightly. So let me just grab some long nose pliers and just bend them out. There we go. And there's only the two, there's no other ones. And now we'll just very carefully pull the VFD from the board. Yeah, it's coming out. And there it goes. No damaged pins. And more importantly probably, no damaged pads on the actual circuit board itself. So now with the VFD actually removed, we can get a good look at the actual components underneath the board. There's the microcontroller with the built-in VFD drive. More on that in a minute. And at the other side here you've got a level translator circuit and some of the other components required to drive the VFD. So everything looks fine. The soldering looks pretty good on all those surface mount components. I don't see anything untoward, so I don't think I'm going to touch anything. I think we'll just offer up the new VFD in place and solder it down. So the first thing I'm going to do is I'm just taking a bit more of a detailed look at the spacing between the legs, and they're actually splayed out very slightly, as you can see there. So I'm actually going to bend them in slightly to make them line up just that little bit better with the holes in the board. And the way I'm going to do that is use the actual work surface, and I'm going to just bend them over very slightly like that. If you do it like this, doing them all at the same time, they're all going to be of equal alignment after you've bent them in. If you just try and bend them one by one, you'll never get them all lining up. So there we go. I might have bent this row a little bit too much because they're pretty easy to bend, but we'll see how it goes. So getting the orientation right first of all. Wow, you do need to bend them quite a bit actually. There we go. And there we go. That's it dropped into place. And it's sitting right down as far as it'll go. So now I'll go away and solder it into place, and then we'll proceed to give a test. Okay, we're all set up again, ready for power up. Now, one thing I didn't bend in those retention tabs there on the brackets because the glass isn't as wide on the new VFD, so there's nothing for it to hold in place. So I've just left them the way they are, with no problem there. So I'm all hooked up. So let's put power on and see what happens. Right. There we go. Yes! And we've got power up. And importantly, it's actually quite bright off camera. And even more importantly, I've now got a lower segment drive right the way along that bottom row there. As you would have seen in the last video, that whole row of segments A, B, C, D, I think it was. Segment D drive right along there was not working at all, but this is working. This appears to be working just nicely. So let me put the actual board into the front panel just very quickly, and let's see what it looks like through the smoke perspex. Again, I'm just holding everything in very loosely in place. Let's put power on. And off camera there, it's not too bad. I wouldn't say it's bright. I have seen brighter, but certainly it's a lot better, a lot brighter than it was, and it's crystal clear, not a problem. So one thing I'd like to mention, I sort of hinted on it earlier, and especially in the last video, is why is the display electronics referenced up to, I think did I say the minus 18 volt or the plus 18 volt supply? I can't remember, but it's the electronics on the front panel, including the level translators, the microcontroller, etc., are not referenced to the same 0 volts that the main processing electronics that you see here is. You've got the microcontroller, the RAM, the ROM, etc., the A to D converter, everything there, and this is a floating logic here. The ground 0 volts on this section of the board is not tied to earth on the actual case of the multimeter. It's floating, but the connector here that goes away off to the display board, the 0 volts on there is tied to the 0 volts, this floating 0 volts ground on that section there. But also you've got a plus and minus 18 volts that comes from the power supply circuit right next to it, up through that display board connector to go to the display as well. And it's on the display board is where there are differences in detaching the display board from the same ground effectively as the main processor electronics, and I thought I'd try to explain why that is. I will also mention the GPIB connector here and also the serial connector here, etc., are also floating. They're detached from the main processing electronics. This section here is ground based referenced, and in order to do that it's got its own bridge rectifier, and it's got a couple of opto isolators where their serial data goes back and forward from the microcontroller on the GPIB section and the microcontroller on the main section, so it's totally isolated. You can see there's a big isolated section right down there, and the reason for that is because the GPIB section will be ground referenced. That's the same on just about all other test instruments. Your GPIB connector, your 0 volts on there will be referenced, and that gives a common reference point for all your test equipment and all your hookup of all your GPIB connectors that may go to multiple devices, multiple test instruments on your workbench. So let me bring in a sketch and we'll get back to this display board and why it's effectively detached from the ground. So here's the schematic for the display board. I think I said in the last video there is actually two versions of this board. This is the older version I happen to have on this multimeter, so it's a slightly older schematic, and you can actually see that it's not entirely clear to look at, but it's dated June 1992. You've got the display switches here, you've got the main microcontroller there, more about that in a second. You've got the actual VFD, and you've got some level translator circuits and power supply circuitry up here. So let me bring in a sketch. So in this version of the board, what you've got is a plus 18 volt supply from the main board and the main 0 volts from the main board as well, coming up through that connector up onto the display board. Then you've got, off of the plus 18 volt supply, you've got a 4.7 volt Zener diode, a forward bias diode, and that effectively, via this 2.61k resistor down to the 0 volts on the main board, creates a 13 volt supply. and the difference between 13 and 18 is 5 volts. This is effectively the 5 volt supply that goes to the rest of the display board. This positive 13 volts now becomes your 0 volts, and your 18 volts becomes your plus 5 volts. Now there's a couple of reasons for that. I think if we look down at this sketch here, I've drawn up the actual microcontroller that's used on this multimeter and the actual VFD itself. Now this is a rather special microcontroller because it does actually have a direct VFD drive in it. You don't need any other circuitry effectively, you just need to wire up the VFD pins directly onto the actual microcontroller itself. So therefore the microcontroller needs to have the right voltage levels in order to drive the VFD. And on this particular VFD, it's plus 18 volts to turn on a segment and minus 18 volts to turn off a segment. And you've also got the filament bias section I've drawn down at the bottom here, which comes directly from the transformer. In this case, I think it's a 12 volt AC filament bias supply. So over on the microcontroller itself, you've got this 18 volts and the 13 volts effectively giving you your 5 volt logic supply to the microcontroller, but you've also got a plus 18 volt supply, a 10 volt Zener diode giving a 8 volt supply to V pre, a pin on the microcontroller, and V load is tied directly to minus 18 volts. I'm not going to go into how V pre and V load works. You can actually look up the data sheet if you like for the microcontroller, and it does offer a little bit of explanation of what that's for. But at the end of the day, what that then gives is the microcontroller all the voltages necessary in order to drive the VFD directly, as I said, separately from the filament bias supply. Now there is actually another reason I think that they've done it this way. You could maybe argue, why not just tie that directly to 5 volts and that directly to 0 volts? Well, I think there's a good reason for that. If you go back to the sketch at the top here, what you will see is that this 5 volt supply that's now being generated effectively, it's not ground referenced, it's not referenced to this 0 volts. So therefore, any noise, any switching, etc. on the display board, especially when you're looking at a VFD and quite a bit of current consumption on that VFD, you could argue that if the microcontroller was tied directly to the 0 volts, any noise generated up in this part of the circuit here is probably going to find its way back onto this 0 volts, the return path for all the current consumption on the display board, and therefore because this 0 volts on the main board is also tied in with the A to D converter, etc. on the main board, you really don't want noise finding its way down onto that part of the circuit. So by lifting this 5 volt virtual ground effectively up towards the 18 volt supply, generating your new 13 volt supply, you do not any longer have a direct return path. It will find its way there eventually, but it's going to be somewhat filtered through this 2.61k resistor and the local decoupling that's done across that 5 volt supply there. So right, I think I'm ready to put this multimeter back together again. It's been a couple of weeks, so let's see if I remember how it goes back together. So there it is, the Agilent or HP 34401A is back together again. I've given it a quick test in the various modes, and I've got it currently hooked up to my PDVS2 Mini, and as you can see there, 10 volts, it's just about 10 volts on the display there, so it looks like the calibration's intact, no problems there. So I'm going to keep this one, I think. I don't think I'm going to sell this one. I think it'll just slot in nicely to the rest of the test gear that I've got. I've been wanting to play around with the GPIB on this multimeter to make sure it's fully compatible with my GPIB app that I've got. I've never actually had a 34401A before, so it'll be nice to have this one around the workshop, another 6.5 digit multimeter. Thanks for watching.